talking now. So yeah, we can talk afterwards if we need to, or tomorrow, or not tomorrow, next week, whenever. But yeah, feel free to, if, because, yeah, well, let's just go on. So did you have any trouble computing the Laplace transforms? Get that out of the way first. So this is 7.1. There we go. Any issues with that? Or was this just easy, too easy? It was too easy. You just want the quiz. Okay, so, but what about numbers 1 through, did you have 1 through, I forget what I'm kind of out of it today. The first few? Yeah, 1 and 5. Those were okay? You're just integrating over a smaller domain. You're not going to infinity. So that wasn't too bad. 1 and 5, 5. Ooh. Well, okay. All right, well, the one I have on the quiz is much easier. It's just a simple step function, more like number 1 than anything. But so why don't we give this a go? Most of what's on the quiz is the stuff like the other ones where you're just looking things up in the table. So this will give us some practice. We'll go over the practice, and then we got some new stuff. The new stuff is easy as well. So today's a pretty easy day. I've been told that we need to get out early so we can go enjoy the sunshine. No sunshine. It should be back soon? Okay, we'll do our best. Here's some here. There's a few. There's one. I guess I'm just going to give these to you one at a time. Enough. Matthew gets one. None of the Coopers are here. There you go.
Question.
Yes.
We didn't go over the formula where we differentiate with respect to SDDS.
Oh, we're doing that today. You mean the derivatives? Yeah. We'll do. Oh, you want? I don't know why I threw that out there. Did everyone get one? Yeah. Wait, that wasn't on your homework, was it?
No, it wasn't. It was just like before. There was.
Oh, there was a formula somewhere. Yeah. No. Yeah, I think we have that today. The derivative, the formula for derivative. So I put this up on the screen. Okay. Am I recording? Yes. Here we are. Dun, 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 dun. There we go. Okay. Hmm. Okay. Just the Cooper's not here. Oh. All right. Hopefully you're coming down the home stretch. But if you are still working, that's fine. But if you're ready, I could take what you have. Nice. No one's ready to. There's a couple of you are like, yeah, it's super easy. Very nice. I know you want to study it more. You're all set. Looks pretty good. Nice. Nice job. All right, you're happy with it? Good job. Yeah, you can meditate if you want. Or you could just give it to me the way it is. Like that. That looks good to me. Oh, you want to give it to me the way it is? Sure, why not? All right. Let's see. Nice. I wish you would. Go ahead.
Sorry, my.
No, they're just finishing up a quiz.
Yeah, I just got my notebook got teared up in my book bag.
Is that going to be thick enough tape?
Just wondering. I didn't want to be rude. I didn't want to interrupt your class.
Oh yeah, take as much as you need. If you want, you can take it out into the hallway and make your repairs. Yeah, they're doing a quiz now, so
I'll take it.
yeah, you can do what you need to, man. You don't need two of these. All right, you're all set. You had boxes. I figured you must have been done, but you're just studying. That looks pretty good to me. Coming down the home stretch. Good job. I see you've got boxes as well. You just don't like yours? You don't like that one? I don't know. Doesn't look terrible. Yeah, that looks great. Oh, these for me. Very nice. Just boxing it up. Is this some sort of instant camera you have here?
It was from homecoming.
Okay. All right. What do you think? Close enough? All right. Looks good. Looks good to me. Very nice. And you're just doing the last one. You can do it. Yeah, just copy it down. Do it quick. Don't even think. It's better to just write. That's not Clash Royale. What is that? Oh. Oh, you're all done. Sorry. I was making fun of his Brawl Stars or whatever he's got there. Oh, do I have all the quizzes? No one's yelling at me. Okay, we're going to staple these together. Okay, let's see what I got. See if it's right. So the first one, a little annoying, but it wasn't terrible. If you've got something like this to start, even if you can't do an antiderivative, I'll probably be like, you got most of it, and just take off a half a point. But this is the full version, and I saw some of you factored, which was really nice. Wait, what was the factoring? I don't know. Yeah, there's like factor out the 1 over s. But yeah, something like this is good. And then the rest of these, it's mainly just copying down what's over here. So like the Laplace transform of sine of 6t is this. And then the next one, you're using the cosine, and you're using the t to the 6th, which is right here. Here's the cosine. Yeah, so that was a little annoying, the 2160, or it's 3 times 720, 3 times 6 factorial. This was a little annoying because I didn't do the algebra for you, but that's what it should be. It's not on this list, there is a trick to dealing with that, like, so that you wouldn't have to do what I just did, but you might as well just expand it, and there it is. And then the last one was pretty straightforward. You've got e to the 3t and hyperbolic cosine of 3t. So there they are. Okay, so your job today, our job rather, is to figure out how to go the other way. Now, here's the goal, and I know that this is going to strike fear in your heart when you see it, but our goal is to do this one. So I don't want to do that one first, though, because I think some of you probably know what is in our future. I know, yeah. So, but we're going to deal with that one. It's not going to be terrible. We'll do it. We'll just save it down here. But like, if I were to say, so here's what I mean by this. If I were to ask, okay, what's the opposite? Let's say I asked you, what is the inverse Laplace transform? So of this function, you would be able to tell me, because didn't we just do this? In fact, we did. Look at this. That is the Laplace transform of e to the 3t plus the hyperbolic cosine. So the inverse Laplace of this should be e to the 3t plus the hyperbolic cosine. That's what we're doing, is we want to be able to go the other direction. So this is like, the Laplace transform is when you're taking something in the normal world, putting it through the wormhole and going into some alternate universe. And then the inverse Laplace transform, you're in the alternate universe and you're going to push it back through the wormhole and get back to real life. So we need to be able to do that in order to solve our differential equations. So that's the goal for today. Let me find the PowerPoint, and then we will eventually, that's the final thing we're going to do today. Hopefully we'll get to it. So let's go. Yeah, inverse transforms. So inverse transforms is exactly what you would expect. It is as easy as you would expect. As long as you can recognize, oh, that's too many words. As long as you can recognize these things, you can go the other direction. In fact, I don't even bother on the exam putting the table of inverse Laplace transforms, because it's just this. That's it. Here's what I mean, is notice that here are the inverse Laplace transform, the table for, I don't know what the yellow thing is doing there, but the inverse Laplace transform. So you have, just for example, this yellow thing has the cosine of kt is the inverse Laplace of s over s squared plus k. Well, isn't that basically just this? So why do I need to make two tables? I mean, I could, but basically this one, they're the same table. It's just like, this is the real world, this is the alternate universe. And so however you want to write it is fine. So you already know how to do this as long as you have your hands on a table like this. So, and you will, because I'm going to give you one when we get to the exam or the quiz. So not to worry, I'm not going to leave you hanging when it comes to the Laplace. You don't have to have these memorized. However, you probably will have some of them memorized, like this one. You do this enough that you're like, yeah, it's so easy. You'll have it memorized. So let's take a look at this, see how you do with these. I want to find the inverse Laplace transform of 1 over s to the 5th. So let me do this. Actually, do I have a bunch? Yeah, I've got a bunch here, I guess. Wait just a minute. Yeah, okay, that's fine. Yeah, I don't have a bunch. I just have this. Okay, that's all right. So this one, here we go. Here's what we'll do. Make it nice. Go ahead and see if you can figure it out while I copy this and put it next to the table. Hold on a sec. Here's my table up here. There it is. See, I've got my nice table. I'm going to slap this thing in here. There. Good enough. Yeah. Well, I'll have to, I'll get rid of the stuff below it. Yeah, give me a minute while I do that. So yeah, it's A and B there. You can ignore all the rest of the stuff here once I get myself squared away. Okay, that stuff is gone. This stuff is going to go too. That's beautiful. Okay, so first one, inverse Laplace, 1 over s to the 5th. What does that look like? Now, I know you're not going to be able to use it exactly, but I'll bet you can figure out which one of these it's going to be, it looks like, even though it's not a perfect match. Mariah, which one of these does that look like, the 1 over s to the 5th? T to the n, because you have n factorial over s to the n plus 1. So this is going to be some sort of a t to the n probably. So now we just have to figure out what value of n. So Caden, do you know which value of n we're going to use for this? Yeah, you're right. N equals 4 because you have s to the n plus 1, so that's s to the 5th. So probably it's going to be t. Whoa, that's huge. Just a minute. Let's try again. T to the 4th. So probably this, but it's not going to be, that's not a perfect thing because you know that the Laplace transform of, so this isn't the most efficient way to do this, but we'll do it this way this time. And then in the future, I'll show you a quicker way to do this. So let's see. So Madison, can you tell me what the Laplace transform of t to the 4th is? Using this formula here. Okay, very nice. So you've got 4 factorial, which is 24, over s to the 5th. Perfect. So this is the Laplace transform of t to the 4th. That's not exactly that. So how are we going to, I think you know how we're going to fix this, is instead of doing this, what I'm going to do is I'll do this. The inverse Laplace transform of 24 over 24 times s to the 5th. Which is the same as 1/24th times the inverse Laplace transform of 24 over s to the 5th. So you can do this because Laplace transforms and inverse Laplace transforms are calculus things like integrals. I mean, that's what the Laplace transform is. It's an integral. And so you can take a constant that is a multiple and you can move it outside either the Laplace transform or the inverse Laplace transform. So either way this works. So now I've got this, and so normally you wouldn't necessarily write this. I'll show you the shorter way to do this. But so you think, okay, what does this represent? And then how can I make this look like that? And then now all I have to do is say, okay, that's t to the 4th. So the final answer for this is t to the 4th. Oh, sorry, 1/24th. After all of that, I forgot my 1/24th. 1/24 t to the fourth. Very nice. All right, let's see if we can do the second one. Or are there any questions about that one? I'll give you another example in just a minute, but if you're happy with it, we'll move on. So what about that second one? So the second one, what does that look like? So letter B, if you had to categorize that, which one? So pick one out of the bunch. And then we'll pick a volunteer here. Rachel P., what do you think? Which of these? It's over here somewhere. Very nice. It's sine of kt. So this will be sine of kt. So let's go ahead and we'll do the same trick. We'll say, okay, if this is the Laplace transform of sine of kt, let's pick a, whoa, what am I doing? Sine of, let's see, what should k be? Let's see, I'll bet you can figure it out. Austin knows what k is for this. So Rachel wanted us to use sine of kt, which is this, to do this. So what would you like to use for k? Very nice, square root of 7, because here you say, well, this k squared should equal 7, so k should equal the square root of 7. So let's actually do that. The Laplace transform of radical 7 times t. So let's do this. So notice I'm kind of doing it the hard way. We'll go and do it the easy way in a minute. But so let's do, oh yeah, sorry, I don't know why I put that there. Let's get rid of it. So I need to know the Laplace transform of this so I can know what I need to do to fix this up here. So we're not quite ready to do letter B. I'm just experimenting right now. But don't worry, I'll show you the quicker way to do it in a minute, which you probably can figure out. Joshua, what is the Laplace transform of radical 7t? So that's the difference, isn't it? Radical 7. It's that radical 7 plus 7. So if you notice, what I'm being asked is to figure out what function this is, but what I'm thinking about is a function that gives me a Laplace transform of radical 7. So here's the way I would do this is I need to do the inverse Laplace transform of 1 over s squared plus 7. So here's the actual thing that I would do. Give me a sec here. Move this out of the way. So if I were approaching this from scratch I wouldn't probably write that down. I would write this, and then I would say this. Okay, well that, I know I need a radical 7. And so let's put that radical 7 in there. But you know the deal is you can't just invent a radical 7 out of whole cloth. You have to balance things out. And so this radical 7 has to be balanced with a radical 7 down here. Now I'm happy because I have something that I recognize from the table. Like I said, I wouldn't necessarily write this down, but it might be helpful to just think about it. Or maybe it's something that you would jot down on a piece of scrap paper, but however you want to do it is fine. So it can be in your head, or it can just be on a piece of paper, or you can just not write it at all. However you do it, though, what you're going to get is 1 over radical 7 times the sine of radical 7 times t. And that is the function in the real world that corresponds with this function in this alternate reality. It's almost like, who is the guy that Benedict Cumberbatch? Dr. Strange, yeah, that's it. He's like doing all these weird things going on. Anyway, yeah, so that's why that's sort of in my mind, that's what I think of when I think of, I don't think of Dr. Strange actually. That just hit me now. But I always think of, that this is some weird world like Narnia, and this is the real world. And so you're going through some sort of a weird wormhole or whatever to get over there. And then you got to get yourself back. So anyway, there it is. So let's practice just 2 more. Let me see if I can grab the table here so that you can have some practice? Yes, I can. Give me a sec. It's going to take me a sec to get this set up. see, do this and this. Get rid of that. Okay. Okay, let me put this somewhere. Yeah, there's that still hanging out. That scares me. Okay, we'll put it right over here. This is good. So paste that in there. There's our table that we like. And then we'll do this. We'll do 2 just to practice. So we have the inverse Laplace transform of 5. Oh, I don't like 5s. Of 8 over s to the 9th. So do that one. And then do this one. The inverse Laplace transform of s over s squared minus 10. So try both of those. And here they are. Just to, well, might as well have one more. Well, this one is so, well, we'll do it anyway, because it's so easy that this is the one that'll make you happy. 11 over s plus 4. There. This one, the last one is actually super easy. So that at least it's one that'll make you happy. Let's see, 244. Ooh. There you go. I don't know how you're doing with this one, but let's see how Adric is. Adric, you got this first one for us? Excellent. T to the 8th. So you got an 8 factorial in there, right? You got to deal with, so the correct, so what you wish that there was 8 factorial up here, right? But it's just 8. And so we need to fabricate. So what we're going to need to do is multiply this by 7 times 6 times 5 and so on. So let's do this. I'll just multiply this by 7 factorial, because 8 times 7 factorial is 8 factorial. And then I'll just do this, 1 over 7 factorial. So that's one way to keep things balanced. So if this is what you did, great. If not, you might have actually calculated 8 factorial. What is that, 40,000 something? I don't even know it offhand. But I know 7 factorial is 5040. So, but you might have actually computed 8 factorial and said, oh, I need to multiply by another 5040. But whatever the situation is, you're going to end up dividing by 7 factorial, which is 5040. So 5040. So there's that one. Okay, next one's a little bit easier, thankfully. So Matthew, did you get this next one here? All right, but I'll bet you can pick out of the bunch which one corresponds with this one, right? So tell me which one that's going to, at least which of the functions over there, even if you don't have the final answer. The cosine, the hyperbolic cosine, is that what you said? Yeah, so notice the difference, just so that everyone sees. The regular sine and cosine have a plus down here. The hyperbolic sine and cosine have a minus. So if you have a minus, that's hyperbolic. If it's a plus, it's the regular. So this is the hyperbolic cosine because of the s up here. So this will be the hyperbolic cosine. Now we just have to figure out what to put in the parentheses. And the parentheses, what's going to go in there has to do with that k. So the k times t. Thankfully, this one, we aren't going to have to make any weird algebra. But Haven, do you know what goes inside the parentheses there for the hyperbolic cosine? Yeah, radical 10t. Nice work. So radical 10 times t. And that's it. So thankfully, I always love it when I have a cosine or a hyperbolic cosine, because neither of those require any gymnastics in terms of the k. See, it's this k up here that causes problems with the sine and the hyperbolic sine. And it usually, we end up having to deal with some weird factor. But here, nothing. Okay, let's do the last one. Like I said, the last one was super easy. It's kind of a softball, but might as well do it anyway. Once I find someone to do it for me, Andrew can do it, right, Andrew? What is this going to be? Very nice. So it's e to the at. Can you finish it up for us? Do you know what a is in this case? Very nice. So negative 4t, and then the 11 is just going to go along for the ride, isn't it? So it's 11 e to the negative 4t. Beautiful. Now, there are a few little glitches. I know, of course there are. There's always glitches when you talk about differential equations or math. So what are those glitches? Well, here's one. This isn't that much of a glitch. It's just something I wanted to point out. And it's something that seems to cause, like when back in Calc 2, like my Calc 2 students have so much trouble with functions like this. I don't know why. They just forget that you can separate this into two functions. And so that's what we're going to do. This is actually two separate functions. We're going to do the inverse Laplace transform of negative 2s over s squared plus 4 plus the inverse Laplace transform of 6 over s squared plus 4. So if you ever have a linear function on top of a quadratic, you can just separate it like this into two separate functions like this. So that shouldn't be that big of a deal. And I don't know if you want to take a guess as to, without me showing you the list, or maybe you remember the list. I can put the list back up in a minute. Or maybe I'll put the list up. Can I put the list up? Here, I'll put the list up here. There's the list. Okay, let me put the problem up. I know I got to toggle now. Okay, so here's the problem. Okay, so I'll tell you who's gonna. I've got my randomizer here. So we got Zechariah. Zechariah wants to do the first one. Okay, Zechariah. So there it is. I'll put the table up in just a sec. So the first one there, you see it? There it is. And then here's the table. Okay, so do you see which one it's going to be? There's the function. Just the first of the two. Go back to the table. So notice that it's got, this one has s squared plus 4 in the denominator, and you've got an s up there. So it's the s in the numerator that's the key. Which one has a s squared plus k squared in the denominator and just s in the numerator? So you got one, Zechariah? You're shy about it? No? I don't know. No, you don't want to do it? What? Oh, you do have it?
I do have one.
Oh, what do you got?
Here.
Yeah, just tell me.
Cosine h of 2it.
Okay.
Negative 24 divided by 2i.
2i? What do you want a 2i for? Oh, you're doing the square root of 2. Oh, okay. Yeah. No. Let's, no, it doesn't. Cosine, no, it doesn't. Yeah, no. Okay, here. There you go, here. It's that negative 2 that you're fixating on. The negative 2, just ignore take the negative 2 out. Negative 2 doesn't matter. So it's just s over s squared plus 4. Yeah, that's an s. I hate 5s. Look here. This here is an s. That's the same as this here. Okay, so that's your problem. Okay, whatever. Let's. No, I get it. Fine. That was a great idea to go for the I. I like it, and actually, you know what? I take it back. It would have worked.
If it was a 5, it would have worked.
Yeah. You could go to imaginary numbers, but we're not going to do imaginary numbers in here. So, yeah. Okay. Let's have Max take a crack at this one. Do you see this one? Okay. Do you know what it is, or do you want me to show you the table? Oh, what do you got? Okay, yeah, it's cosine of 2t. So yeah, it's supposed to be a s. I try my best not to have any 5s because I can't draw them correctly. So yeah, so we're using the cosine. So look at the cosine there, s over s squared plus k squared. Yeah, if you use imaginary numbers, it'll turn it into a minus, but whatever. Anyway, where did my thing go? So that is going to be negative 2 times the cosine of 2t. Wow, let's see. Can we handle this one? Maybe we'll never get to the really hard one. Hooey. Okay, so this one, let's see if we can. Now that's a 6. There are no 5s on this page, just so you know. So let's see who gets to do this. I know you all want to. Okay, I think I've almost looped around. Claire, what do you think of that one? Do you recognize that, or do you want me to show you the table? Very nice. 3 sine of 2t. So I'm going to do a little bit. I should have, just a sec. I'm going to get rid of this arrow. Give me a sec here. Okay, the arrow's gone because I probably should do this. So you do 3. And then this is going to be 2 over s squared. That was a beautiful connection there, is that this thing, because it's a sine, that's the one that causes a lot more grief because you have to worry about the numerator having the right number in it. But Claire did a great job of picking the right number because this is 4, which is 2 squared. You better have a 2 up there, which is what I did here. Whoops. And so this is going to be 3 times the sine of 2t. Very nice. And that would be in our current numbers. All right. Let's see. What do we have next? Next is the monster that I've been avoiding. Okay, so let us switch back here so that I can do this because it's going to take a lot of effort. So this thing. So in order to do this, I'm going to use a technique that you learned and you promptly tried to block out of your memory because it was so painful, but it's coming back for a second go here, and that is partial fractions. Oh, yes. Okay, so I don't remember how you, I don't know how you learned partial fractions, but I'm going to show you the trick, at least one way to deal with partial fractions. Really, oftentimes it's going to be painful, but I'll do the best I can. So partial fractions, what you do is you set this thing up. Every linear factor gets its own fraction. So you have 3 factors here, and we're going to have 3 fractions like this. So far, so good? Sure. Now what happens, and this is the shortcut that I usually do, but if it bothers you, you can write it out. What we're going to do is we're going to multiply everything by the common denominator. The common denominator is this denominator here, is it not? That's the common denominator. Now here's where I'm going to skip a step, but hopefully you'll forgive me. And that is, I'm not going to write that out. I'm just going to write the result. So if I multiply everything by that common denominator, on the left, I will have s squared plus 6s plus 9. On the right, I will have a times these 2 factors, because when I multiply the right-hand side by that common denominator, the s minus 1 will cancel with the s minus 1 underneath the a. In a similar fashion, the s minus 2 will cancel with the s minus 2 under the b, which will leave you with these. And then finally, the s plus 4 cancels with the s plus 4 under the c. It still looks like a nightmare, doesn't it? Well, there's another shortcut that I like to use. This doesn't always work. So let me just mention the correct way to do this. So the correct way to do this, the painful way, is you multiply through, you collect like terms. That is to say, if I were to multiply, I would have a times s squared plus 2 times a times s minus 8 times a. And then I'd have a similar trinomial here and another trinomial here. I could collect together all of the s squareds, which I think is as squared plus bs squared plus cs squared, collect them together and say that together they should equal s squared. A plus b plus c equals 1. And then you could do the same thing with whatever your coefficients of s and whatever your constants are. However, there is a shortcut which you may have learned, maybe you didn't. Here is the shortcut. The shortcut is to do this. Plug in the values that will make each of those three denominators equal to 0. So if I plug in s equals 1, watch what happens. I get 1 plus 6 plus 9 on the left is equal to a times negative 1 times 5 plus b times 0 times 5 plus c times negative 1 times 0. Whoa, wait, sorry. I think I have that backwards. C times 0 times negative 1. There it is. There. So all I've done, you see, here's the deal, is that if this is true, then it will be true for every value of s, including s equals 1. So I plug in s equals 1 and see what happens. So that's the sort of shortcut trick. It is not foolproof, though. It is possible that this will give you, well, it's not that it'll give you the wrong answer. It may lead you astray in certain situations, but none of those situations will be situations that we come up against in this class, I don't think. Anyway, this is going to be 16 is equal to negative 5a, which means that a is negative 16 over 5. Well, we could do the same thing with s equals 2. So let's do this. So let's make a little line. So once again, you could use algebra. If you've learned how to do partial fractions the correct way, there's nothing wrong with that. It's just this is a little bit shorter oftentimes than the correct way. And correct, I'm using correct in quotes because this is correct. It will work under most conditions. There are certain conditions where this fails to work, but if we bump up against those, we can always just do it the old-fashioned way using algebra. Okay, well, anyway, when s equals 2, here's what I'm doing is I'm plugging s equals 2 into that red equation, the monster equation up there. Whoa, what just happened? How can I go back? Yeah. So then when s equals 2, I get 4 plus 12 plus 9 on the left, a times 0 times 6 plus b times 1 times 6 plus c times 1 times 0. I think I did that right. So I'm plugging s equals 2 into all of these factors. And let's see what happens when I add all this stuff up. 16, 25, I think. Is that right? 25 is equal to 6b. So b is equal to 25/6. So see how convenient this is? I mean, you could do this using the algebra, and you can imagine, especially with the answers being these ugly fractions, that in all likelihood, the algebra would have given you something extremely ugly. And then the last one, I'm going to use what would have given me a 0 in the denominator of the final fraction, which was s equals negative 4. So when s equals negative 4, what happens? And once again, I'm just going to copy everything from the numerator, or not the numerator, the red up there, and I'm going to put s equals negative 4. So 16 minus 24 plus 9. So let's see, I'm going to just 0a. We know it's going to be 0a and 0b. I mean, that was the whole point, is that this would be 0 and this would be 0. So, I mean, just might as well get to the end here. And so then that would give me, let's see, negative 4. So c times negative 5 times negative 6. Does that look right? So I'm just changing all the s's to negative 4s. And then that's going to give me 1 on the left and 30c on the right. So c is 1 over 30. Wow. Let me pause for a minute and see if this, here just a minute, I got to zoom out just a bit. Wow, so much. So much to do here. All right, any questions about that so far? So you can do the partial fractions. Now, here's the beautiful thing about the partial fractions. Once you have them, then this Laplace transform is almost done. This becomes A, so notice that this A is associated with S minus 1, so that would be negative 16 over 5 times the inverse Laplace of 1 over S minus 1. And then the B, so I've kind of skipped a step here. I should have written it as negative 16/5 divided by S minus 1, but I'll just factor out the negative 16/5. It'll make things a lot easier. And then B, we have 25/6 times the inverse Laplace transform of 1 over S minus 2. And then the final one was 1/30. I know it's off the screen, but you remember. I'll show it to you in just a minute. 1 over S plus 4. Now that I've got that, the rest of this is super straightforward. Negative 16/5 times e to the t. You say, where'd the e to the t come from? Well, it came from this table. So if you look down the table, okay, I'll go find the table. There it is. Wait, there it is. There's the table. So 1 over S minus A, 1 over S minus 1 is e to the at. So S minus 1, A is equal to 1, so that's e to the t. So we've got that. And then the next one is 25/6, 25 over 6, e to the 2t. And then 1/30 e to the negative 4t. All right, while you're digesting that, I need to double check one thing and make sure that everything is going to be okay for your homework. Hold on a sec. Give me a sec. I've got your homework here somewhere. Where is the homework? Homework. Oh, I don't have homework yet. Haha. Okay, everything will be okay. Because I need to add the homework, apparently. Is that really true? No, there's homework there. Never mind. Homework for Monday. Let me check the homework for Monday. There's just one thing that I want to make sure is not. Yes, I need to make an edit, I believe. 35. Yeah, the 35 through, just check here. Yeah, 35. All the high numbers. I'll edit this right now so that you don't have to worry about it. But not to worry. So we haven't done the derivatives. So we'll do the derivatives on Monday because that's where we actually can use Laplace transforms to compute the solution to a differential equation. That's where the power is. Right now we're just doing background. It's like, how do you measure things? So I'm fixing the homework so that it's just the stuff we just did. So do the best with this stuff, and then on Monday we'll do the derivatives. So derivatives are coming. All right, I'm going to stop the recording if you want to